So in this video we will see about the Cortex M0 plus, the processor. See, so far we have been actually learning about the Raspberry Pi Pico RP2040, which is a microcontroller, but now we are going to see about the processor that is present inside the microcontroller. We have already discussed that each microcontroller will have its own processor, right? Like Arduino has Atmega. This RP2040 has Cortex M0 plus processor. Okay, so in this unit we will be seeing about that. In addition to that, we will also exclusively learn about NVIC, which is nested vector interrupt controller, like how we have seen in the previous video. Then we will also see about MPU, very important topic, memory protection unit, and then we have debugging, and then we also see GPIO. In addition to that, we also have DMA. This is a very important concept. By the second part of this unit will be DMA, direct memory access. We will see that in the next videos. So these are all the things that we are going to see one by one. There will be few repetitions, but I hope you will see through it. So Cortex M0. Cortex M0 is a processor which has very low gate count. That means that, or you can consider that it is being implied that having low gate count will have very high energy efficiency, and it is a microcontroller mainly made for embedded applications and in area where low power is expected, right? So we can consider this as a low power embedded application oriented processor, right? That is why Raspberry Pi, they have used Cortex M0 in their microcontroller, right? So by the end of this particular session you will be able to discuss the future of this Cortex M0 plus. Okay, these are all the features. I know this is going to be very plain, but still, when I say tight integration, uh, the peripherals, as you have seen in the block diagram, almost everything is very tightly associated with each other, so that you can get things done very easy. Okay, uh, let's say there is a shop. Okay, there is a grocery shop. If you want to buy vegetable, you will go and buy that. If you want to buy a pen, you'll have to go find a stationery shop. If you want to buy something else, for example, if you want to buy fresh meat, you'll have to go find a butcher shop. But if you take a supermarket, everything will be available inside, right? There will be a area for meat, there will be an area for grocery item, there is an area for bakery items, right? Everything is placed very near to it, so you can easily access it and get things done, right? So that is what they mean here by tight integration. All the hardware is very tightly integrated. And then second point, thumb instruction. Thumb instruction means our microcontroller, our processor is 32-bit, so which can process 32-bit of information. But we can also program our processor in such a way that I can give the instruction in 16 bits. So that we will call it as thumb. Right? So when I say thumb instruction, I can give the instruction in 16 bits, so that instead of giving one instruction in a place, I can give two instructions in a place. So I can get things done very fast. Right? That is another advantage or wonderful feature in this Cortex M0 plus. Then next one is single cycle input output, which we already discussed before. It will help us in getting our things done, the execution done in single cycle. So we have a dedicated hardware for that. Right? So we have seen in one of our previous video that Raspberry Pi Pico has dedicated hardware for multiplication, that is integer multiplication, integer division, and then we also have for interpolator, right, for interpolation. So that's what is here. Then power control optimization. We have power control optimization, where the controller can put itself into power control mode by gating certain architectural power connections. Okay, we call it as architectural gating. I can stop, or I can get certain hardware and I can restrict the power flow to that, so that I can have a optimized power control. Okay, we have so many hardwares inside this particular microcontroller. We have I2C, SPI, PWM, so many things are there. Let's say I'm using this particular processor based microcontroller for a very simple embedded application which does not require PWM. So in that case, I can do architectural gating, and I can restrict the flow to Usually it doesn't happen, but I'm giving just an example. Right? You can restrict things and you can reduce the power consumption. Then the third one is, the last one in this area is integrated sleep modes. We have integrated sleep modes. We have different modes. One is one is sleep mode. Then we have deep sleep mode. So in sleep mode, the processor will put all the hardwares to sleep so that it will not do any work, so the power supply will also be conserved. Then there is something called as deep sleep, where almost everything will go to sleep except the set of registers which will wait for event signals. There is a signal called as wait for event, so it will wait for that. Once that signal is turned on, the processor will return on. So you can put your microcontroller that is based on Cortex M0 into sleep mode as well as deep sleep mode. That way you can conserve the energy, right? And then we have fast code execution. This is also something very important. Maybe I'll share another interactive visualization that will help us in understanding. But now try to visualize any information that you give will be converted. Okay, remember I told Python is a script based language, so it requires interpreter, right? So interpretation has to happen. So any information you give has to be interpreted, and that interpretation has to be converted into the code. So any information that is getting is actually fetched, decoded, and executed. Fetch, decoded, executed. Fetch, decode, execute. So that is how the execution actually happens. So here we have a pipeline structure in such a way that when the first instruction is being executed or decoded, uh, the second instruction will also be fetched. So what happens is, at a particular time, two or three things can be done simultaneously. You will have a fast code execution, right? And then we also have optimized code fetching. So there will be an optimization where by which there will be a little time advancement through which you can get things done much more optimized. And then we have a hardware multiplier, which we have seen in SIO itself. In SIO we saw hardware divider, the same thing here but for multiplication. So imagine you are multiplying two numbers, 25 into 25. Okay, when you do this multiplication, what your processor does is, inside the software, where the processor, what it does is, it will add 25 plus 25, then 25 plus 25 plus 25, that is 125, again 125 plus 25, 150, 150 plus 20, like this it will do 25 such iterations to get the value 625. Whereas if I take a hardware, it will directly multiply and give me the answer. So what I have done is, I have my main processor. Along with that, I also have an extra hardware which will do certain multiplication, so that I don't have to burden my processor. So things can be done simultaneously, and this will give a better and fast execution of the processes, right? Then we have deterministic high performance interrupt. Deterministic, when something is done, deterministic in sense, we have allotted certain thing for certain interrupts. So it is deterministic. You don't have to go find where to do what is one. It's already predefined. Okay, that is the one advantage. We call our interrupts here as NVIC, nested vector interrupt control, and it is deterministic. And similarly, our instruction cycle is also deterministic. And then we have system level debugging and serial wire debugging. So you can debug directly on the processor. Okay, you can bypass the microcontroller peripherals, the bus fabrics, and you can directly touch the microprocessor and get things done.